location. But it's convenient to blow up.
Well, you can map memory to 0
Yeah, yeah,
on Intel processors.
true.
My check's just saying it hasn't said.
Modern versions of Linux will block it by default.
Do they? Okay.
Because if a kernel module, like due to some bug, tries to execute a null pointer and
Mhm.
have your code mapped to 0, then it will
Okay.
run the kernel will run your code.
Yeah.
So,
Cool.
to avoid that, they block it by default.
Yeah. Yeah.
Do we have to do any error checks for the file?
You can assume the file that I'm going to test with is correct. I'm not going to put bugs in it. I'm not going to have missing data or things like that. But if when you update the file, you write something that's incorrect, right, that will still cost points. So, but the file that I start with will be guaranteed to exist and have at least 3 nodes in it, right, a question and 2 answers, and be formatted correctly and all of that. So no error checking like that. Yeah.
For when we're manipulating the tree
Mm-hmm.
and we get to the end and it's an answer and the user says no,
Mm-hmm.
that's when we ask them for a question and
Right.
another answer.
Mm-hmm.
How do we treat those? Like,
So you've been moving down through your tree. And let's say at this point there's an answer. So these are all questions. And this is some answer. Let's call it A1. Okay, so is A1 correct? And the user says no. Okay. What's the correct answer? And the user says A2. Okay, give me a question. Where, for example, yes is A1 and no is A2. And you can do it the other way if you want. And so they give you some question. Okay, so what you want to do is, instead of having this answer here, make a new node with whatever this question is, and have this be A1 and this be A2. Okay, so you want to turn this tree into this tree, which means you got 2 options. One, if you actually have access to this node, not a copy of it, but you actually have access to that node, you can change, if there's a flag in there, change it to say it's a question instead of an answer. Change the text to be this question. And right now, this node's left and right children are null. Set the left child to a node containing A1, the right child to a node containing A2.
yeah, the user is giving us a string, right?
Which string?
Like, how do we treat that text? What the user is entering? Like, you can't,
This text?
yeah.
That becomes the text of this node. So what's your node look like? What's your node structure?
Left, right, and a flag.
So you've got a left, you've got a right, you've got a flag. Anything else? Some sort of data, right?
Yeah. Yeah.
Okay. So what does the flag mean?
Question and an answer.
So false is an answer?
Yeah.
So normally you're here, right? The flag is false. The data is whatever you guessed as your final answer, left and right or null. Okay, so go into this node, change the flag to be true, so it's a question, change the data to be whatever question they gave you, change the left child to be a new node, and in that node, set the left and right to null, set the flag to false, so it's an answer, and set the data to whatever the A1 answer was. And then set the right child of this node to another new node, A2, right? Set left and right to null, flag to false for an answer, and data to whatever the correct answer A2 was. So you just take the pieces and put them together and build up this little 3-node tree, right? And basically replace this incorrect answer with that tree. Make sense? Cool. You had your hand up, now you gotta ask a question. No, I'm kidding.
I don't know if it was the thing you do after class or.
What kind of problem?
So I've got x minus 1 mod 15,
Mm-hmm.
and when x is 0, I expect it to return 14, but it's returning -1.
Oh, bad mod function.
Exactly. I think I'm doing it wrong.
How
Maybe
negative
just
can x get?
X is mod 15.
So x
So
is
it's
always between 0 and,
0 and 14.
so just add 15 to x and then do mod 15.
Okay.
And it won't change your answer, but it'll force it to be positive or 0.
So why is it let it do that?
I thought modulo was supposed to be like a modulo, like in the number theoretic sense, but I guess not.
No,
Okay.
it's different.
Yeah.
So that's a good answer.
Is there an operator that forces it to
There might be a math
give you a proper?
Like math 11.
Yeah, so just add the moduli to it. But if it's arbitrarily negative, you gotta do more work.
Well, it's not arbitrary.
I mean, if you wanted to convert negative 1,000,000, you can't just add 15. You gotta do something fancier.
Wait, it's always way too.
But if you know the most negative it gets is -1, you can cheat it.
Okay, cool.
All right, other PA4? I may as well get a network connection because I always end up needing one.
Maybe. That doesn't have anything to do with it. I'm doing this once. But yeah, that fixed it.
All right, so yesterday we were looking at the socket class. And when you construct a socket, you give it an address and a port. Your address is typically a quoted string with a 4-part IP address or a host name or something like that. Your port is just an integer. And it returns a socket, and from that socket you can use get input stream, get output stream to get streams that you can read from or write to. And when you push stuff into this socket, it talks to a socket at this address bound to this port number. And we played around with this using a server that was running. So let's make a server. So this was our client, and we were taking input and just shoving it out to a client. So all right, so when we want to be on the other side of the communication, we want something called a server socket. And we construct a server socket by just giving it a port number. So when we construct a server socket with a port, we basically create a socket, and the terminology is it's bound to that port number. Okay, it means that there's a endpoint of communication on our local machine associated with this port. So create a server socket with port 1210. There's a port numbered as 1210. And anybody anywhere that can connect to this machine, right, can make a socket, bind it to this address, and ask for port 1210, will be requesting a connection to this port. Okay, this socket. And it's up to you whether you want to accept that connection or not. So on the server side, it's a two-step process. You create a socket, and then you accept connections on it. And when you accept a connection, this will basically create a new socket, which is connected to the client socket. So let's just do this in code. So let's make an echo server. So I'm not going to worry about standard in. Server socket. I'll just call it SS. And we're not going to do port 22, we're going to do port 1220. Okay, so new server socket 1220, that creates a socket that can be used to connect, to accept connections. So, and we're just going to loop forever. Alright, so we're going to print out a message, say we're waiting for a connection request, and then we'll call the accept method, and that will block. Okay, we'll sit inside accept until somebody tries to connect to port 1220, at which point we'll get a socket, which is now connected to basically a pipe with the client on the other end, and we'll print out a message saying that we received a connection, and we'll print out that socket using its print string method. And then let's do some I/O on that socket. So we'll get an input stream and make a scanner out of it. We'll get an output stream and make a print writer out of it. And let me just make these from client and to client. And then we'll loop. So, well, we have another line coming in from the client. So we'll call next line, save that in a string, print it out here so we can see what the client sent us, and then let's send a message back to the client. so we'll just echo that back. We'll do our flush to force it to go to the client immediately, and we'll just loop. When we get down here, we know that something happened and the connection closed. Client exited. And let's just go back to the top of the loop, and we'll sit here forever. There's our whole server. Okay, so we're going to create a socket at port 1220. We're going to listen for connections. When a connection comes in, we'll accept it, set up our scanner and print writer, and we'll start reading in from the client one line at a time. We'll print out here what we got from the client, and we'll send it back to the client with a message saying you sent, and their text in angle brackets. When the connection shuts down, we'll just say the client exited, and we'll go back to the top. I should probably close the scanner, but I'm worried about exceptions, so we're just going to do this. Let's see how bad. Hey, not bad. All right, so there's our server. So let's talk to the server. I'm going to use Telnet. You can use PuTTY if you're doing this on Windows. So we'll Telnet to localhost 1220. And there's a message on the server saying it received a connection from 127.0.0.1, port 5268. And the local port is 1220. That's on the server side. And we accepted the connection over here. So Telnet, whatever I type, should get sent. And it will actually get sent immediately. It doesn't wait for enter. But since we're doing next line, we'll be reading one line at a time. So this is a test. And so the server says we received this is a test from the client, and it sends back the message you sent. This is a test. All right, so Telnet, when you want to get out, you do control right bracket, and then you can do a Q to exit. That closes the connection, and the server noted that the client exited, and it's gone back to where it's waiting for a connection request. And so now if I Telnet again, it repeats the process.
What happens if you try to connect from another?
If I try to connect from another one, it will block. Oh. It does not block.
Does it echo?
So I've made the connection request. The server socket is still there, but the server is not executing that accept statement, right? So the server socket's still there. It's still 1220, but it can't actually process any of this until it gets back to the code where it says accept. So this was our original one. Once this one exits, then this one over here should get responded to.
So it keeps track of the backlog?
Well, it's being buffered up. We send it, we flush it, but I don't know where it actually is in the operating system. It's somewhere. It's being buffered in the JVM, so here's what's happening. So let's quit this. Oh, we're running Telnet. Okay. So yeah, Telnet's buffering it up. If we had our own server code and we tried to connect, the connection would not proceed, right? So that should be 1220. So this should be where we're blocking, right? And so you can type stuff in, and it's just sitting in your buffer waiting for something to ingest from system.in. So on the server side, what's the issue here? The issue is we're sitting in this loop, right? And we won't actually create the connection until we say accept. So in PA5, right, you want to be able to perhaps handle multiple connections, which means you want to be able to continue accepting even while a conversation is taking place. So this is more threads. So what does your main method do? Something like, do some initialization, set up a server socket. Accept a connection, which gives you a socket to communicate with the client through, and then create a new thread, which basically reads from standard in and goes to a socket, and create a second thread which reads from the socket and sends to standard out. And you go right back and you wait for another connection. Alright, so if you don't do this, if you just have one thread for one direction and your main program handles the other direction, you got one conversation at a time. But if you want to do multiple conversations, yeah.
It's interesting with multiple conversations, this would totally accept multiple threads and maybe be able to say, oh, this person said this, but how would you want to send to, if you started to send to people and you had multiple people connected to you?
So if you were doing this with
this would
a,
send it to everybody.
so if you had like a GUI front end, right,
Sure.
you could pop up a JFrame that has a area, you type in an area where you see messages, right, and so these two threads would pay attention to that. Then another connection request comes in, you pop up a new JFrame, and it's only working with that socket.
That's
Right.
a nice idea to have new window each.
Yeah, but the alternative is to do, you know, one server talks to everybody, different people can talk to the server, right? So like a help desk
Yeah, that was the
setup.
first window.
And if you do this in Eclipse, right, you can get multiple console sessions popping up. And you can type in one and it will be associated with that process. If you do this on the command line, it's really funky. Because if multiple things try to read some standard in, sometimes they just round robin. Right, so you can write a program that reads from standard in and does something and throw it in the background 5 times. And then just start typing and see who ingests it. And that's fun. Right, so if you do this, your main program is basically always accepting connections. And you might want to do things like keep track of how many connections you have right now, instead of just blindly going up and accepting another connection. Why?
If you have too many, you could slow something down.
Yeah, so someone could just come in and try to make, 10,000 connections to your server, and that can ruin your day. And then shutdown is interesting, right? So if the client exits, then when you try to read from standard in, you're going to get an end of file. So this thread will know when the client has exited. This thread will not know until it tries to send something to, this thread will know when something exits. Because when you try to read from the socket, it'll say that that's no longer there. But this thread won't notice it until it tries to write to the socket, which will only happen after you try typing something in and hitting enter. So you kind of need some sort of communication. So you might want to do an interrupt or some kind of signal. So that gets interesting. But those are embellishments, right? Not strictly necessary.
In the main, I don't remember if you went over this. Can you cut a thread from main before you disconnect?
Oh, what do you mean cut it?
Well, I guess maybe when the main stopped looking for a connection because you put this program, it could also tell the first thread to stop.
You can send a message to it through a variable, for example.
Sure. Okay.
And you can also do
I
a
can see.
wait in here and pause yourself until the thread exits.
Okay.
So there's different ways to do that. But like I say, all the fun ways are deprecated. Or you could just say like kill. But
You can do that.
you can, but you're not supposed to. Okay, so this makes sense? Okay, so the server side is almost identical to the client side. The only difference is you create a server socket and you accept connections, and what you get back from that accept is a socket. And then it's the same game as on the client side, basically. You have a socket, the client has a socket, they're connected to each other, either on the same machine or across the network, and you do the same things you did on the client, right? Get some input and output streams and use those. And there's different ways to do this, right? Scanners and print writers are very particular things. They're very cooked objects that we're constructing here. You could do binary I/O, right? And there's lots of different kinds of streams. There's data streams. There's raw streams. There's streams that are intended to be sort of byte oriented. Scanners and print writers are fairly high level things, right? Scanners let you say, give me the next double. Print writers let you take any string and put it out there and throw a new line on the end automatically and so on. If you were doing some sort of low-level processing, right, you'd probably want to be sending just straight binary data, and probably not one character or one line at a time, but maybe, you know, a large block of 10,240 bytes or something like that. And so there's other methods that we could use, but it all starts from a sock, right, from a socket, and you can get a stream from that and then turn it into other kinds of things. For what we're doing, scanner print writer will work fine, right? And I think those are the only ones I'm going to hold you responsible for, unless we go crazy next week and talk about I/O. But make sure you know how to use scanners and print writers. So questions on any of this? I posted this code up to the shared area on Canvas just as samples, so there's a client-server pair. All right, so let's talk about Lab 5. So Lab 5 is optional. It's 50 bonus points in the lab area. And you get to work with another group. Okay, so you're doing your labs in groups anyway. But for Lab 5, you want to get together with another group because you're doing something that involves 2 Raspberry Pis. Okay, so you got like super groups. But you want to develop both sides of Lab 5 as a group. Don't just say I'm going to do the send and that group will do the receive, right? Do the whole thing because it's a good exercise. So this is the other end of the spectrum for doing network communication. Lab 5, you're doing everything yourself. Okay, you don't have sockets, you don't have server sockets, you don't have print writers, you don't have anything. Well, almost nothing. What you have is 3 wires, and that's it. Okay, so you're going to get 2 Pis, you're going to connect the ground lines between them together. Okay, so pin 4. And yeah, so pin 14 gets connected between them. And then pin 16 and 18 are going to get connected between the two pies. So you got 3 wires, and that's it. That's your whole network. Okay, there's no Wi-Fi built in on these pies, by the way. So here's what we're going to do. Ground we don't worry about. It's just there so that we have a common reference for what a 1 or a 0 is. Because if I just take my pin 16 and connect it to your pin 16, and I put 5 volts on my output, and you read that input, you might see 5 volts, you might see 3 volts, you might see 30 volts. Okay, you got to have a common ground reference. If it's a very long wire, you're going to see something radically different, and it's probably going to move around. So we connect the ground line 14 just to give us a common base, and then we basically have 2 lines that we can share information on. So we're thinking of these as a data and a clock. And one side is going to be responsible for writing, the other side is going to be responsible for reading. So this is unidirectional transmission. If you wanted to do bidirectional, we'd take another pair of lines and we'd hook them up in the other direction, or we'd modify our protocol. So the clock line is normally low. And while clock is low, the system is quiet. We're not transmitting any information. Okay, so here's the protocol.
Probably be able to see this.
Okay, I guess. So here's the protocol. Suppose we want to send a 1. You raise the data line to a 1, and while the data line's high, you pulse the clock. Okay, that's transmission of a 1. If you want to send a 0, you drop the data line, and while the data line is low, you pulse the clock. That's your whole protocol. That's 99% of your protocol. So to read information, you look for this rising edge of the clock, and you read the data value. So on the receiver side, we've got a sender and a receiver. Okay, this is what the sender is doing. They're controlling the data and clock. How do you do that? It's like lighting LEDs. Right? Your LED labs, you learned how to put 5 volts or 0 volts on a pin, so that's what you do with these 2 pins. Set this pin to 0. If you want to write a 1, set that pin to a 1, then set the clock to 1, then set it to 0. On the receive side, you know how to read the voltage level on a pin. That's what you did with your switch, lab 4. So you read the clock line, and you should be normally reading a 0. The first time you read the clock and you see a 1, immediately go and read the data. And if you see a 1, you're being sent a 1. If you see a 0, you're being sent a 0. And then don't do anything until the clock goes back to a 0. And then go back and do this all again. So you don't want to continually check the clock and say, oh, it's a 1, data's a 1, I got a 1. And then check the clock here, oh, clock's a 1, check the data, I got another 1. Check the clock here, it's a 1, I got another 1, right? You're not getting multiple 1s. You're only getting a piece of data on the rising edge. So this is what you did when you were debouncing your switch. You're paying attention to the change from a 0 to a 1. Is that clear? So it's all edge triggered action. So that lets you transmit and receive a single bit. And if you can do that, you can do everything. Okay, you can reinvent the modern world as long as you have a way to send 2 bits. So get this working first, right? And details to worry about. Remember 250 setup and hold time? So setup time says the data has to be stable a certain amount of time before this clock tick. Okay, it takes time to transmit information. It takes time to raise the gate voltages on the receiving side and so on and so forth. So make sure you set the data line to the correct value, and then you wait a little bit of time. Now, how long should you wait? If you wait 5 seconds, that's plenty of time, but it's going to be really slow transmission. If you wait a nanosecond, that may not be enough time. So you're going to have to play with it, right? Make it a variable. Wait a certain amount of time, and then raise the clock. And then, how long do we need the clock to be high? Again, you can make it as long as you want, but the longer it is, the slower your transmission rate. But if you make this too small, here's what can happen. So the transmitter raises the clock line. The receiver is in a loop. Okay? The only way you can detect this clock is by polling. Just keep reading the clock input port. Read it, check it, it's a 0. Read it, check it, it's a 0. Read it, check it, it's a 1. Now we do something. But it takes time to go through that loop, right? So the danger is you read the clock line over here, it's a 0. You read the clock line over here, it's a 0. You read the clock line over here, it's a 0, right? And you've missed the clock edge. So if this is too narrow, you might be transitioning too fast for the receiver to notice it. So you got to make it wide enough to guarantee that the receive code can get all the way through the loop, right? Worst case, it just read it. It's got to do some if statements, do some looping, so on, get back up there, read it again. You've got to hold it high for at least that long. And then similarly, there's a hold time after the clock to make sure that if you notice the clock right here, but you don't actually get around to reading the data until over here, you'd like to know that edge is still, that level is still correct. So this has got to be wide enough, this has got to come early enough, and it's got to change late enough. So that's typically setup time, hold time, and that's your pulse width. And start off making them generous, right? Put them in the millisecond range and you'll be fine. But if this clock is a millisecond, right, you're limited to 1,000 characters per second, pretty slow. But make it generous and then try to dial it in. Okay, so that's the first thing, transmission of a single bit, reception of a single bit. If you can do that, now you put your bits together to make words. So the protocol is characters get sent least significant bit first, total of 8 bits. So when you first run your receiver, wait for a bit, whatever bit you get, put that right here in bit 0 of some character. The next bit you get, put it in the next position, do that a total of 8 times until you've received 8 bits, treat that as a character. So print that out on your display or save it in a file or whatever it is that you're trying to do. The next bit that you get, the 9th bit, that's the least significant bit of your second character. And you just keep reading bits, and every time you've gotten 8 of them, you've received a new character. And typically just go ahead and print that out.
How would you do that in code?
Which
Like,
part?
bit by bit? Because
So
you wouldn't be able to do that.
there's shift operators in Java. So you
Okay.
can shift things left or right 1 bit. So you can either use a mask, right? Start off at 1 and shift it left each time to refer to another bit. And if you want to set a 1, you can OR with that mask. So you can do bitwise ands and ORs instead of logical. Or you can start in the most significant bit and shift your number that you're building over to the right. And that's slightly easier.
I need to do that.
But for starters, just print out each bit and make sure you're getting the right
Sure.
bits. Yeah,
Would it be easier just to add the bit you read each time and then just shift one to the left?
yeah. Except you're starting with least significant bit.
Yeah.
So you need
and
to,
1 is the least significant.
So I get if you add
Yeah.
1, but then
Add 1 and then you shift left, and then add either 0 or 1 and then shift left.
yeah, that's what you're saying.
then I think your number ends up backwards.
Make sure, right? No, I get you, because you're shifting left, so now the one's safe. You're saying the same thing he's saying, I think.
So if you're going to do that, I would set the most significant bit and then shift to the right. So your first bit is here, and then shift to the right. Put the second bit there, and then shift to the right. Put the third bit there, and when you're done, you should be in the right order.
Wait, so when you shift, are you shifting the number under you, or are you shifting where you're looking?
You can do it either way. So
Oh.
this is assuming you're shifting the number that you're building, right? You're building a
Yeah.
character bit by bit. If you set the most significant bit of that character for each bit you receive and then shift the character to the right, this should leave you with your character. The other option is take the bit that you receive, shift it to the left, and OR that with your character. So the first bit gets ORed right here, the second bit gets ORed right here, the eighth bit gets ORed right here.
Yeah, because if you do move yourself, see, okay.
And I prefer doing that than shifting to the right, because shifting to the right with negatives, sometimes you get sign extension issues, but it's good stuff to mess with, right? Yeah.
So for the clock signal,
Mm-hmm.
why do we only trigger on like rising edge? Why can't we change the, or like, why is it more common to have it like clock high, they have it read, and then we go low, and then they read again, and we go high, and then
You can do that.
You
But
know-
what do you,
would you happen to know why that's not common?
so partially because maybe it's a power issue because you're asserting a signal, and if you're not sending any characters for an hour, you're outputting a high clock needlessly. That would be my first guess, but I don't know if that's
Maybe
true or
there's
not.
some analog thing.
I think
Um,
that would be
but-
one
but-
error.
Like DDR memory, right, basically does something like that. It shifts in on both the rising and the falling edge, right? So that's where the double data rate comes from. So I mean that is something that's a real thing. But this is about the most simple version of a protocol that we could imagine. It's actually pretty close to something called SPI, Serial Peripheral Interface, and it just adds another data line to receive. All right, so we're slightly over time, but I need to mention one more piece of information, which is the sync pulse. The big problem with this kind of approach is if something happens and the receiver, say, misses a data pulse, the way that you're packing these bits into characters will be off forevermore, or until you get 7 more of these sync errors. So there's a protocol for sending a special pattern of clock and data line transitions which says, I want to reset all of our counters back to 0. Okay, and that's called a sync pulse. And the way we do a sync pulse is raise the clock and then pulse the data. And this is normally not a valid thing to do, right? The data is supposed to be stable for the duration of the clock pulse. But if you see the clock line go high and the data line is low, keep sampling the data line until the clock drops. And if you notice a pulse in there, that's saying, I want to resynchronize. So whatever you're doing internally to build up your characters, reset your counters back to 0 so that the next bit that you receive, the next valid bit, becomes the least significant bit. And if you do this frequently, in between every character would be extreme, it will take care of these framing errors, okay? So as you crank the speed up, you may find that you want to do the sync pulse more often, but you can start not worrying about it and see how it works. And your goal ultimately is, transmit War and Peace from one pi to another or something, and do it across a few wires, see how long you can get these wires to be, and how it affects the noise and the speed and so on. So it's a big experiment. All right, so we're a minute over, but I was late, so there you go. I will see you next time. Come by my office at 11 if you want. That's my last hours before PA4 is due. So you can catch me there. Otherwise, I will see you tomorrow.